This is going to be the lecture of the last section here in 28. So it'll be section 28.8. We're going to be looking at the electron microscope. So an electron beam can be used to form an image of an object in exactly the same way as a light beam. So while reflection, and refraction are used to bend light rays, electric and magnetic fields are used to bend an electron's trajectory. Just as the resolution of an optical microscope is limited by the wavelength of light, the resolution of electron microscope is limited by the wavelength of the electrons. Since the wavelengths of the electrons are much shorter than those of light, the resolution of electron microscope is typically thousands of times better. So this electron microscope is an interesting example of the interplay between wave and particle properties of the electrons. The electron beam can be used to form an image of an object in exactly the same way as a light beam. So you got a ray of light is bent by reflection or refraction. An electron trajectory is bent by an electric or magnetic field. Rays of light diverge from a point on an object can be brought to converge by a converging lens or concave mirror. And electrons diverging from a small region can be brought to converge by an electrostatic or magnetic lens. So these figures here can show the behavior of a simple type of electrostatic lens. And the third figure is going to show an analogous optical system. In each case, the image can be made larger than the object, so both devices can act as magnifiers. So you've got an electrostatic lens for an electron microscope. You got an electrostatic lens here, and you can see part of the mechanics of how this works. And you've got an electrostatic lens again here for an electron microscope. All of these are different methods by which you can take information and try to focus it at a different point. So electrons accelerated by a certain potential have de Broglie wavelengths several orders of magnitude smaller than photons of visible light. The electron microscope creates such energetic electrons and then focuses them with magnetic and electrostatic lenses onto specimens. Biologic materials sliced into thin sections can be examined in the electron microscope, producing images with far better resolution than is possible for the light microscope. Individual macromolecules can be imaged by these means. So the photograph shows a beautifully arranged alternating thin and thick filaments of muscle. The diameter of the thin filaments is about 7 nanometers, and the mycosin filaments are 10 to 11 nanometers thick. The bracket on the left indicates the region of overlap between the actin and myosin molecules. The right bracket shows the region containing only myosin. In other words, these areas. The major uncertainty in using this technique is the degree to which the sample is altered by necessarily elaborate preparation for examination in a high vacuum system. So how is it superior? The resolution of an optical microscope is limited by the diffraction effects. Using wavelengths in the visible spectrum, about 500 nanometers, an optical microscope can't resolve objects smaller than a few hundred nanometers, no matter how carefully you make the lens. The resolution of an electron microscope is similarly limited by the wavelength of the electrons, but these may be many thousands of times smaller than wavelengths of visible light, and as a result, the useful magnification of an electron microscope can be thousands of times greater than an optical microscope. So you got a few questions there that you can answer and whatnot, but hopefully you've enjoyed this particular chapter.